Hello, everyone. Welcome to the 2024 SNIA Compute Memory and Storage Summit. My name is Andy Walls. I'm an IBM Fellow and the CTO for our Flash systems. Today, I'm going to talk to you about something that we call inline anomaly detection, maybe better known as ransomware detection. I think we're all aware that cyber attacks are on the rise, and I'm sure that you've seen some highly publicized ones. Unfortunately, about 51% of cyber attacks are ransomware or exfiltration, and they're increasing all the time. Unfortunately, the cyber criminals are well trained. They view this as an income opportunity, and they are part of organized crime. So, about twice as many occurred in 2022 versus 2021. And in 2023, it was 2.5 times as many. Unfortunately, about 66% of these breaches were not identified by the organization's internal security teams and tools. That is not to say that those security teams and those tools are bad or are not doing everything they can. It's just that these criminals are extremely intent on hurting our society and getting income no matter what it takes. So we have to do everything we can. If you look at the steps to data resilience for storage, it really all starts by security and data protection. It's extremely important that we continue to improve our network security, that we continue to predict, we continue to have SOC integration and protect from infrastructure failures and natural disasters. So you kind of look at it as at two parts. We've dealt with disaster recoveries for decades, and we've gotten pretty good at it as long as the organizations practice testing and have good disaster recovery protocols in place. Now, unfortunately, cyber attacks are different. We don't always know when they happen. First and foremost, we need to have immutable copies that cannot be mounted. They are truly immutable. At IBM, we call these safeguarded copies. And these copies they're stored on the storage arrays themselves. In fact, you need to have two people agree to delete it, and you even can set it up so that nobody can delete it. In other words, they just expire based on settings that you established at the time of the snapshot. Now, this is important, but it's not enough, because for you to know that you need to go to one of these snapshots, you have to discover that there is an attack. Now, ideally, you've discovered it on the perimeter. You've not even allowed the cyber criminal into the networks. But unfortunately, we all know that this sometimes happens. And when it does happen, it's extremely important that we find it early so that we can go back to one of those copies and that we can recover and restore with as little data loss as possible. And for this to work, we have to have automation and testing. We have to have simplified operations. It has to be easy to do and tested all the time. Now, at IBM, we use our own SSDs, and we call them FlashCore modules. The importance of FlashCore modules really is that they are not SSDs. They are computational storage devices. And we've talked about computational storage for quite a while. At IBM, we actually have shipped it since 2017. Where we began was including transparent compression. And the importance of transparent compression is not just compressing the data. You'd think, well, that is the key. No, if you're doing software data reduction, you can get compression assists and accelerators like Intel's QAT, and this can compress the data for you. But what's really takes the compute and what really can hurt the performance is the metadata you need in order to remap the data and store it somewhere else. Because obviously, if you compress, there's less data. You can't write it to the place that the host had written it to. You're going to combine many of these compressed objects together and then store it out to the data at a new place. Well, you've got to have metadata to show where you've mapped that data. And if it gets overwritten, you have to delete, you have to invalidate where it was stored and create new metadata for where it's written to now. And then the really expensive part is you got to do garbage collection. You've got to invalidate the data. You got to delete the data that was stored and has been overwritten. And you now use those locations to store new data at. Well, this process is very complicated, especially if you're doing it in the controller that is removed some from the underlying NAND flash. With the FlashCore module having the NAND flash right next to the SSD controller and having to already do garbage collection, because of course with NAND flash, you cannot write to it until you've erased it. It's actually straightforward to put the compression in because the garbage collection is already there. You can merge these two processes together and you compress the data, which actually helps your garbage collection because now the garbage collection is working on compressed data. And you're only doing it in one place, the garbage collection. So it has worked out extremely well by putting the compression into the FCM and having the storage controllers completely having the compression transparent to the controllers. It's worked out very well. And it's a great example of computational storage. And so as we were looking at the success of this, we were determining, well, what else can we do with the computational storage that's in the FCM? And at the same time, the ransomware and other malware, as we talked about, it's just has become an epidemic. And I realized that every part of the stack needs to do its part. We can't just rely on the outer perimeter. We can't even rely on AI to help determine if somebody has broken in, because unfortunately, AI is also going to be used by the cyber criminals to help them determine how and when they can break in to a network. So every part of the stack needs to do its part. And for a long time, people thought, well, block storage can't do a lot, all right? Block storage doesn't know the context. It doesn't know the operating system. It may not know the file system. And so as we were exploring this, some very highly technical people told me, Andy, there's nothing you can do in block storage. And that actually motivates me. And so I realized that we're actually right next to the data. There are things that we can do. We can scan. There are things that a computational storage device can do to help look for ransomware that takes no performance impact whatsoever. And that is extremely important because some of these things that you have to do to detect if the ransomware has occurred takes a lot of computational resources. So we started doing research into how ransomware affected the systems containing FCMs. Here's an example of a very well-known ransomware trace called WannaCry. And we ran this ransomware on a flash system with FCMs. We were running a workload and then injected this ransomware. And the pink over here is when the ransomware was running. It wasn't running here, and then it ran again here. The green shows the entropy. This is Shannon entropy, and the higher the entropy, the more random the data. And you can see, for example, here is very interesting. It is encrypting, but it's not encrypting everything. It's not at its very highest 8.0. And and so it's not it's choosing what it encrypts. It picks the files, but you see a heavier workload. This is showing the IOPS over time. Eventually, it stops for a while. You can see the entropy is less for the workload. Then it begins again. And you can also see here various other attributes about the workload. And in the end, we discovered that 28% of the data modified after the attack. Now, we did this with many other pieces of ransomware as well, and we wrote our own ransomware simulator called Wanna Laugh. And so we learned how ransomware was affecting the workload. We also looked at an LBA scatter plot. And this is a the y-axis shows the LBA address range, and here for this application is where the boot records are, and the ransomware is not attacking that. It's not attacking the OS because it wants you to be able to boot. It's affecting the data, and you can see over time it is progressing through part of the LBA range. And so if you statistically put that together in histograms and stuff, you can compare to normal workloads, and this also can help determine if it's certain types of ransomware. So after all of that research, we started looking at what statistics we could gather in the FlashCore module that we could then send to a machine learning algorithm and start to learn what ransomware looks like as compared to real workloads. And we ended up with about 40 different statistics. These range from Shannon entropy, as I mentioned before. They include even chi-squared. They include the LBA addressing and sequencing patterns stored statistically, changes in the read and write throughput, the compression statistics, because we know what the compression was for this block, so we can compute the compression as it comes in, and we now know the delta. We know how the compression changed. And so we're looking at this on every single IOP. And the beauty is we have no performance impact whatsoever because we do it in the FPGA. We do it as we are compressing the data and bringing the data in. And that allows us to do this on the side without creating any kind of performance impact whatsoever. And it's really thanks to the computational storage offload that's built in to the FCM. So as I said, we calculate the entropy in our latest FCM that we call FCM4 and that we've released to the field. We have this now running in systems throughout the world in our flash systems. And we keep these statistics on every single IOP. And we have two small RISC processors that are doing the statistical averaging, the histogramming, and other statistics on all of the stats that we are gathering real time. And they're summarizing it in a form that we can then look at. And first of all, we trained a model, and as a result of training that model with many different types of ransomware and simulated ransomware running many different workloads, we were able to get a model, an AI model, that we now load on every single flash system. I call it the revealer. And this revealer is a true AI model. It is it takes up very little resources. It's an inference engine, and it's running on the flash system. But what it's taking as input is the summaries, as I mentioned before, that are on every FCM. So the FCM is gathering the entropy and the compression delta and the other various statistics that I mentioned, like the IOPS, the throughput, the entropy, all of that. And it is sending it to the summarizers that are putting it into the form that every 2 seconds, we read that information in the controller, the flash system controller, and it's doing so for every single volume, and it's doing so on every single FCM, and then it aggregates all of this information into a per volume statistics that is sent to the revealer. And the revealer is this inference engine that's running on one of the cores. And every 2 seconds, then, it makes a decision as to whether it detected ransomware or not. And after a certain voting window, so every 2 seconds, it votes. And then after a certain interval, we look at how many votes for and against ransomware. And if we achieve a certain number of votes in that window, we then send an alert to our Storage Insights, which is our monitoring software in the cloud. And Storage Insights then will alert either support or our customer and tell them that a ransomware anomaly may have been detected. And then the customer will hopefully, as running safeguarded copy, will have snapshots that they can use in order to recover from this event. Now, as all of you know, I'm sure, that something that can happen in security software is what we call false positives. I send an alert, but it really wasn't a ransomware attack. It was a certain operation that the customer was doing, maybe that they don't do very often. So what we do when we get an alert is that we also send an hour's worth of data, every 2 seconds data for every volume. We send it to Storage Insights in the cloud, and then we can train the model based on this data that we're getting to help further isolate, to help improve our false positive and our true positive detection rates. And so it's the FlashCore modules, although they're not doing the AI models themselves, have a key role in this because we offload the statistics gathering to them, and they are gathering every single IOP so that we can do a lot of different statistics for all the volumes and feed that to this model. It has worked out extremely well. And it shows really one of the, I think, very important parts about computational storage. Computational storage is not having the SSDs, or in this case, the FlashCore modules, do everything. It's offloading certain functions that the SSD can do well. The SSD can do these statistics on the side, the statistics gathering on the side without performance impact, and gather them up. But you really don't want it running the AI model because it's only looking at a part of the data. The processing in the flash system controller is much more powerful, and it can run various different models. And in the future, we're looking at a lot of different things that we can do to further improve, especially as ransomware changes. So computational storage really is defining and saying what you should do is you should define what elements are best run on different places. And here, instead of doing everything in the software, trying to compute the entropy, trying to compute the compression differences, which can be very CPU intensive, it's having the SSDs or the FCM do that, and then have the flash system controller running the inference model the inference engine, and defining and helping then to determine if there was a ransomware attack. So it's security is, I think, an extremely high priority place for us to focus computational storage. We have started to ship this. We're getting results back. We're improving our false positive rate. We're looking at the data and training, and we have ideas for where to go in the future. So hopefully this has been instructive. This has been informational, and love to take feedback from you and answer any questions. So thank you very much.